Welcome to Thought Frontier.
Okay, so get ready because today we're going deep into the physics of nothingness.
Nothing.
You've heard the saying, nature abhors a vacuum, right?
Right.
Well, get ready for a plot twist. Modern physics might just argue the opposite,
Yeah.
that nature actually loves a vacuum, throws a party in a vacuum. So by the end of this, you'll not only know how physicists define nothing, but we'll also explore how it might hold the secrets to the universe's beginning and its ultimate end.
Yeah. It's pretty amazing.
Pretty intense, right?
It all starts with understanding how the very definition of nothing has changed over time.
Okay.
We can go all the way back to Aristotle, who believed that a true void was impossible. He thought objects would move through empty space at infinite speed, which obviously doesn't happen.
Yeah, and it's kind of funny to think about now, considering how much effort we put into creating vacuums these days.
It does highlight how far we've come in terms of our scientific understanding.
Yeah.
A pivotal moment in this evolution was Otto von Guericke's experiment in 1654.
Okay.
He essentially sucked all the air out of a copper sphere, creating one of the first high-quality vacuums.
I have to mention this detail because it just makes the story so much better.
Oh, yeah.
The sphere was actually watermelon-sized, not grapefruit-sized, as some initially reported.
Wow.
Imagine two teams of horses trying to pull this giant copper watermelon apart.
Oh, my gosh.
And they can't because of the force of the vacuum inside.
It was definitely a dramatic demonstration,
Yeah.
and it really marked a turning point.
Okay.
From that point onward, the vacuum became an essential tool in physics. It helped us understand everything from the behavior of matter to electromagnetism and even gravity.
Yeah.
But as physics advanced, our definition of nothingness had to evolve too.
So that's where the different flavors of nothing come in.
Right.
Like, each area of physics has its own version.
Exactly. In electromagnetism, a vacuum means there's nothing to slow down light. In gravity, it means there's nothing to warp space-time.
Okay.
Each definition depends on what you're trying to describe. But then quantum physics enters the scene, and things get really strange really fast.
This is where things get truly strange indeed.
With quantum physics, we encounter the quantum vacuum, which is far from empty.
Okay.
It's actually a state of constant fluctuation, with particles and energy popping in and out of existence.
So even when we think we've stripped everything away, there's still this underlying buzz of activity.
Imagine a field like a magnetic field,
Okay.
but instead of having a direction, it has a strength at every point in space.
Okay.
That's a scalar field, and one of these, the Higgs field, is responsible for giving particles mass.
It's kind of like a constantly bubbling sea of virtual particles, right? That quantum foam we hear about.
Precisely. And we have evidence that this isn't just a theoretical idea.
Okay.
When we measure the magnetic strength of an electron, it's a bit stronger than classical physics predicts.
Right.
But when you factor in the influence of this quantum foam, the calculations match up perfectly.
I read somewhere that the measurements match up to 12 decimal places. It's incredible that something we think of as empty could have such tangible effects on the physical world.
The implications of this are staggering.
Yeah.
And it doesn't stop there. Another piece of evidence is the Casimir effect.
This is where the metal plates come in, right?
Yeah.
If you put two uncharged metal plates really close together in a vacuum, they get pushed towards each other.
Yes, because of the pressure of those virtual particles outside the gap between the plates.
So they're pushing the plates together.
And this isn't just a theoretical curiosity.
Okay.
The Casimir effect has real-world implications, especially in nanotechnology, where it can influence how tiny machines operate.
That's amazing. But it also makes you wonder, if nothing is actually this dynamic quantum vacuum, could the entire universe have sprung from it?
Now we're getting to the heart of it.
Yeah.
To understand that, we have to delve into the world of scalar fields and this mind-bending idea of true versus false vacuums.
Here's where it gets really interesting.
Yep.
I read this great analogy about scalar fields in the Quantum magazine article.
Yeah.
Imagine pendulums that can hover at an angle instead of just hanging straight down. That angle represents the field's value.
A perfect analogy.
And just like those pendulums finding their preferred angle, as the universe cooled after the Big Bang, something similar happened to the Higgs field.
Right.
It underwent a change of state. Its pendulum shifted, and that shift is what gives particles their mass.
Exactly.
So mass, this fundamental property we take for granted, is a result of the universe choosing a specific configuration for the Higgs field.
Yes.
But wait, you said something about false vacuums. What does that even mean?
Okay.
Is our universe potentially unstable?
It's a possibility. although a mind-boggling one.
Okay.
The Higgs field might not be in its absolute lowest energy state.
Mm-hmm.
Its true vacuum, it could be in a false vacuum instead.
Okay.
This means there's a chance, however small, that it could suddenly shift to a lower energy state.
Okay, I'm picturing those pendulums suddenly swinging to a new angle and the whole universe going haywire.
Right.
But wouldn't that be disastrous? Wouldn't it rewrite the laws of physics as we know them?
Theoretically, yes.
Oh.
If the Higgs field were to undergo what we call vacuum decay, a bubble of true vacuum would expand at the speed of light. Everything inside that bubble would have the laws of physics rewritten.
This is getting deep. So nothingness could actually unravel everything.
It's a truly unsettling concept.
Yeah.
But thankfully, the time scale involved is incredibly vast.
Okay.
Even if our universe is in a false vacuum state, the chances of decay happening within our lifetimes are astronomically small.
That is slightly reassuring, but this raises another question. If there are false vacuums, are there other types of vacuums out there? Is there a whole landscape of them, each with its own set of physical laws?
This is where string theory comes in.
Yeah.
And it leads to a truly mind-blowing concept.
I need a minute to process that, but lead the way. What does string theory have to say about this landscape of vacuums?
String theory, which attempts to unify all the forces of nature, suggests that our universe has extra dimensions beyond the three we experience. These extra dimensions can be curled up in countless ways, and each configuration could lead to a different vacuum state.
That's incredible. So imagine countless universes, each with its own version of nothingness and its own set of rules. It's so different from the simple void we started with.
It is.
Wow.
And it gets even more interesting when we connect this to the theory of cosmic inflation.
Inflation, that period of super fast expansion in the early universe. How does that tie into all of this?
Cosmic inflation suggests that our universe is just one bubble in a much larger multiverse. As the universe undergoes inflation, it's constantly creating these separate pockets of stability, each with its own potential vacuum state.
So we might be just one bubble in an endless sea of bubbles, each with its own version of nothing. That's a concept that's going to stay with me.
Yeah.
But there's more, right? That Quantum Magazine article mentions something about a hidden dimension that could lead to a collapse.
Right. If a hidden dimension is large enough, a vacuum could actually become unstable and collapse, creating a bubble of true nothingness that expands at the speed of light.
Wait, true nothingness?
Right.
So not even the quantum vacuum, but a region where the laws of physics as we know them just don't apply? That's terrifying.
It's a mind-boggling concept.
Yeah.
It's almost as if Aristotle might have the last laugh, with nature ultimately choosing nothing over something in the grand scheme of things.
Okay, my mind is officially blown. We've gone from vacuums on Earth to a potentially unstable universe in a multiverse of vacuums. And now we're talking about bubbles of absolute nothingness swallowing everything up. It's a lot to take in.
It definitely challenges our assumptions about what nothing really is.
Yeah.
But our journey through the physics of nothing isn't over yet.
Okay.
We still need to explore the possibility of creating something from nothing and delve into some truly mind-bending phenomena like Hawking radiation.
I can't wait to see where we go next with this. Welcome back to our deep dive into the physics of nothing.
Where we left off, we were contemplating the truly mind-boggling idea of universes being devoured by bubbles of absolute nothingness.
I'm still trying to wrap my head around that one.
It's a big concept.
But for now, let's shift gears a bit.
Okay.
You know that YouTube documentary you sent?
Yeah.
It talked about something called the Schwinger effect.
Right.
Where under extreme conditions, we could actually create something from nothing.
Or at least what appears to be nothing.
Right.
Yeah, that's right.
So the Schwinger effect is a remarkable theoretical prediction. Born from the intersection of quantum mechanics and Einstein's famous equation.
Exactly.
Essentially, it states that if you have an incredibly strong electric field, it could rip apart particle-antiparticle pairs from the vacuum.
Right.
In essence, creating matter from nothing.
Okay, hold on.
Yeah.
I thought if we were talking about a true vacuum, there shouldn't be anything there to rip apart.
Remember how we talked about the quantum vacuum?
Yeah.
That bubbling sea of virtual particles constantly popping in and out of existence?
Yeah, like that quantum foam we discussed earlier.
Exactly.
Yeah.
They usually annihilate each other almost instantly.
Right.
The Schwinger effect suggests that a super strong electric field could essentially stretch these virtual particles apart, preventing them from annihilating and turning them into real particles.
So we're not creating something from absolute nothingness,
Right.
but rather manipulating the energy that's already present in the vacuum.
Precisely.
Okay.
It's more about transforming energy from one form to another.
Guided by the mind-bending principles of quantum mechanics and relativity.
And if I remember correctly, the documentary mentioned that scientists have actually come close to observing the Schwinger effect here on Earth.
Indeed.
Really?
Back in 2022, researchers used graphene to create an experimental setup that mirrored the conditions needed for the Schwinger effect.
Wow.
They weren't able to create electrons and positrons as predicted by the theory, but they did observe the creation of electrons in holes, which behaved in a similar way, flowing in opposite directions.
So not a perfect replica,
Right.
but it's still a pretty significant step.
It is.
It seems to back up the idea that nothing in physics is completely different from what we normally think of as nothing.
It really is.
It's fascinating.
And it brings us back to the question of the universe's origin.
Okay.
If we can create matter from the quantum vacuum in a lab, is it possible that the universe itself arose from a similar process?
That makes you think, doesn't it?
It does.
This time we're not just talking about the quantum vacuum, but a state before space and time even existed.
Right.
Where did everything come from?
One of the most intriguing theories comes from Edward Tryon back in 1973.
Okay.
He proposed that the universe could have emerged as a giant quantum fluctuation
All right.
from a state of what he called quantum nothingness.
So the entire universe with all its galaxies and stars and planets started as a quantum burp from the void. That's a pretty wild idea.
It is a wild idea.
Yeah.
It's important to remember that this quantum nothingness isn't the same as the absolute nothing that philosophers debate.
Right.
So when physicists talk about the universe coming from nothing, they're not saying there was absolutely nothing.
Okay.
It's more like a state of pure potentiality with its own set of rules governed by quantum mechanics.
So we're not talking about something popping into existence from absolute non-existence.
No.
More like the transformation of an already existing state into something incredibly complex and vast.
Exactly. A change of state. A shift in the fundamental fabric of reality that gave rise to everything we observe today.
That's a lot to process.
Yeah.
But it still doesn't answer the question of where those laws of quantum mechanics came from in the first place, does it?
That's one of the ultimate mysteries that physicists are still grappling with.
Right.
But before we get lost in the origins of the universe, let's turn our attention to another phenomenon where nothingness plays a crucial role.
Okay.
Black holes and Hawking radiation.
Yes. Black
The
hole.
ultimate cosmic vacuum cleaners.
Not even light can escape those things.
Right.
How does nothingness factor into all of that?
It's a fascinating story.
Yeah.
Black holes, as described by general relativity, are regions of space-time where gravity is so strong that nothing can escape.
So in the classical view, a black hole should be completely silent.
Right.
No radiation, no information coming out, just a giant cosmic drain.
But when we bring quantum mechanics into the picture, things get much more interesting. Remember those virtual particle pairs that are always popping in and out of existence in the quantum vacuum?
They seem to be popping up everywhere in our deep dive today.
Well, near the event horizon of a black hole, which is the point of no return, something amazing can happen.
Okay.
One of these virtual particles might fall into the black hole,
Okay.
while its partner escapes into space.
Wait, so one gets trapped by the black hole's gravity
Right.
and the other gets flung out into the universe?
Exactly.
Wow.
But here's the key. The particle that falls into the black hole has negative energy, while the escaping particle has positive energy.
Negative energy. Now that sounds like something out of science fiction.
It's a real concept in physics, and it's crucial to understanding Hawking radiation.
Okay.
The negative energy particle reduces the black hole's mass, causing it to slowly shrink over time. Meanwhile, the escaping positive energy particle becomes what we observe as Hawking radiation.
So black holes aren't entirely black after all. They slowly evaporate, radiating energy away because of those quantum fluctuations happening at their event horizons.
It's a beautiful example of how quantum effects can influence even the most extreme objects in the universe.
Wow.
But there's another mind-blowing detail about Hawking radiation.
Okay.
It challenges our understanding what a vacuum really is.
Okay, you've got my attention.
Okay.
How does Hawking radiation do that?
Imagine two observers.
Okay.
One is falling freely into a black hole,
Okay.
and the other is hovering just above the event horizon.
Okay.
The free-falling observer sees empty space near the black hole, just like you'd expect from a vacuum.
Makes sense.
Right.
They're in free fall. Nothing seems out of the ordinary.
But the hovering observer, who has to constantly accelerate to avoid falling in,
Okay.
sees something completely different.
Oh.
They see the space near the black hole filled with particles, the Hawking radiation.
Wait, so two observers in different frames of reference
Right.
perceive the same region of space completely differently? One sees a vacuum and the other sees particles.
Precisely.
That's crazy.
This highlights the fact that what we perceive as a vacuum, as nothingness, is relative. It depends on our state of motion.
My mind is officially blown again. It's a lot to take in. So nothingness isn't just about the absence of matter or energy.
Right.
It's also about our perspective, our frame of reference.
Yeah.
It's almost like nothingness is in the eye of the beholder.
It's a deep insight that has major implications for how we understand quantum field theory and gravity.
Wow.
It suggests that our concept of nothingness needs to consider the observer, their motion, and their interaction with the universe.
So even when we think we've stripped everything away,
Right.
there's still this element of subjectivity, of perspective, that shapes our understanding of what's left.
Yeah,
That's a truly humbling thought.
it is.
But it also opens up a whole new set of questions about the nature of reality itself.
Indeed.
Yeah.
Hawking radiation, with its interplay between quantum mechanics and gravity, forces us to rethink some of our most basic assumptions about the universe.
Right.
It leads us to question the very nature of space, time, and even information.
I think we need a moment to process all of this.
Yeah.
But before we do, I have one more question.
Okay.
If black holes can evaporate through Hawking radiation,
Yeah.
does that mean the universe itself could eventually evaporate away too?
That's a question that pushes us to the very limits of cosmology.
Right.
It raises deep questions about the ultimate fate of everything.
Yeah.
But before we get into that, we need to take a little detour and explore one of the most important ideas in modern cosmology, cosmic inflation.
Inflation, that period of superfast expansion in the early universe, how does that connect to the universe evaporating?
It might seem like an odd connection,
Yeah.
but trust me, it all ties together.
Okay.
Not only does cosmic inflation explain some of the most puzzling features of the universe we observe today, it also provides a framework for understanding how nothingness played a role in shaping the universe's evolution.
Okay, I'm definitely curious to learn more.
Okay.
Let's unpack this whole cosmic inflation thing and see how it connects to everything we've been discussing. All right, we're back. And I have to admit, my head is still spinning from all these mind-blowing concepts.
It's a lot to take in.
Black holes, quantum foam, universes popping out of nothingness.
Yeah,
It's been quite a deep dive.
it has.
And we're about to add another layer of complexity with cosmic inflation.
Right?
That's right. Before we went off on that tangent about black holes, we were about to explore how this period of superfast expansion in the early universe
Yeah.
connects to our understanding of nothingness.
Well, the Big Bang model, as successful as it's been, couldn't explain everything.
Right.
For example, it couldn't explain why the universe is so incredibly uniform on large scales, or why its geometry appears flat. It also couldn't account for the absence of exotic particles, like magnetic monopoles, which should have been created in the early universe, according to the theory.
So there were a few things that didn't quite add up.
Right.
Some mysteries that the Big Bang model just couldn't solve.
Exactly.
Okay.
That's where Alan Guth's theory of cosmic inflation comes in.
Okay.
He proposed that a tiny fraction of a second after the Big Bang, the universe went through an insane growth spurt.
Okay.
We're talking exponential expansion, growing by a factor of at least 10 to the 78th power.
Hold on, 10 to the 78th power.
Yeah.
That's a 1 with 78 zeros after it. We're talking about the universe going from subatomic to grapefruit-sized in the blink of an eye.
It's almost impossible to grasp,
Yeah.
but it elegantly solves those mysteries the Big Bang couldn't address. Imagine a wrinkled, deflated balloon.
Okay.
Now, picture suddenly inflating it to the size of a house.
Okay.
The wrinkles smooth out and the surface appears much flatter.
So, inflation stretched out the fabric of space-time, smoothing out any initial irregularities,
Right.
and creating the uniform universe we see today.
Precisely.
Okay.
And because it expanded so rapidly, any magnetic monopoles that might have existed were spread out so thinly that we're unlikely to ever detect them.
Okay.
Inflation also stretched the curvature of space-time itself, making the universe appear flat.
Gotcha, like that inflated balloon.
Exactly.
Okay, I'm starting to see how inflation solves those Big Bang puzzles.
Good.
But how does this tie into our theme of nothingness?
Well, inflation is thought to have been driven by a scalar field,
Okay.
much like the Higgs field we talked about earlier. This
Yeah.
inflating field, as it's called,
Mm.
would have had an incredibly high energy density in the early universe as the universe cooled.
Okay.
This field would have transitioned to a lower energy state, releasing an enormous amount of energy that fueled the rapid expansion.
So in a way, the universe has transitioned from a high energy state of nothingness
Right.
to a lower energy state.
Yeah.
Powered the creation of everything we see around us. It's like all this stuff came from a cosmic shift in potential.
That's one way to think about it.
Yeah.
It's a pretty profound concept
It is.
that connects the physics of nothing to the evolution of the universe on a grand scale.
It really makes you wonder if there might be other scalar fields out there.
Right.
Potentially driving other inflationary events.
Yeah.
Or even the creation of other universes.
That's certainly a possibility.
Yeah.
And it brings us back to that idea of a vast landscape of vacuums, each with its own set of physical laws and possibly its own unique history of inflation.
Okay. I need a minute to let that sink in.
It's pretty amazing.
But let's try to bring some of this back down to earth for a moment.
Okay.
We talked about the Casimir effect earlier.
Yes.
And how it shows that even in a vacuum, there are measurable forces at work.
Right.
Does that mean we could harness this vacuum energy for practical use? I mean, who wouldn't want unlimited free energy?
The idea of tapping into the quantum vacuum or zero-point energy
Right.
is definitely a tantalizing one.
Yeah.
It pops up in science fiction all the time as a source of unlimited power.
Sign me up.
But unfortunately, the laws of physics, specifically thermodynamics, put some pretty hard limits on what's possible.
Okay.
While the Casimir effect shows that we can manipulate vacuum energy to create a force,
Right.
extracting usable energy continuously is a whole other ballgame.
So even with all our fancy technology, there's no free lunch to be had from the quantum vacuum.
Not in quite.
Okay.
While a perpetual motion machine or a device that breaks the second law of thermodynamics by drawing unlimited energy from the vacuum just isn't feasible. The Casimir effect can be utilized in very specific applications,
Okay.
like in the development of incredibly small devices at the nanoscale.
So no zero-point energy-powered spaceships anytime soon.
Probably not. And it's important to be skeptical of pseudoscientific claims about things like propulsionless engines
Right.
that supposedly harness vacuum energy.
Right.
These claims often disregard fundamental laws of physics
Right.
and haven't been backed up by any solid scientific evidence.
Speaking of mind-blowing claims earlier, we briefly discussed the idea of vacuum decay,
Yes.
where a bubble of true vacuum could expand and rewrite the laws of physics as we know them.
Scary thought.
Should we be worried about this?
It's certainly a fascinating concept
Yeah.
that highlights the potential for instability even in something as fundamental as the vacuum.
Right.
Whether our universe's Higgs field is in a true or false vacuum is a question that's still up for debate.
Mm-hmm.
Current measurements suggest we might be in a metastable state,
Okay.
meaning decay is possible. But the timescale involved is mind-bogglingly vast.
Okay.
We're talking about timescales that dwarf the current age of the universe.
So it's not something we need to lose sleep over.
No.
But it does make you think about the ultimate fate of everything.
It's a good reminder that the universe is constantly changing and evolving. And even the seemingly empty vacuum might hold clues to its ultimate destiny.
Well, I think we've explored just about every facet of nothing imaginable.
We have.
From ancient philosophical debates to the frontiers of modern physics, it's been an incredible journey.
It has been a journey.
We've traced the evolution of our understanding of nothingness,
Yeah.
from a simple void to a dynamic quantum foam, a source of particles and forces,
Right.
and potentially even the engine of cosmic inflation.
It's amazing.
We've seen how it challenges our understanding of space, time, and the role of the observer in defining reality.
It really does.
And we've learned that even in nothingness, there's a whole lot of something going on.
Yeah.
The universe is full of surprises, and the more we learn, the more we realize how much we still don't know.
Exactly.
It's both humbling and exciting.
It is.
The physics of nothing is a frontier of knowledge full of mysteries and possibilities waiting to be uncovered.
That's a great way to put it.
To all our listeners out there, keep questioning, keep exploring, and never underestimate the power of nothing. It just might hold the secrets to the universe.